Teragamma motor control technology makes it easy to optimize servo motion for your application. It provides expert assistance and assistance for experts.
Hi, I'm Chris Cullen of Teragamma Motor Control. Making motion easy is no help if the motion isn't exactly what you need. In this video, I'll show you how Teragamma's advanced tools help you to adjust and optimize motion for your application. This demonstration axis is the same kind used for some pick-and-place tasks in electronic assembly machines. It has a test load mounted to the ball screw slide. The load-to-motor inertia ratio is about 3.2 to 1.
The axis has been automatically commissioned, so motion planning is already close to optimal. What does that mean? Let's look at a 1-revolution move. The motor goes from 0 to 8,000 counts. How does it get there? A pulse of acceleration brings the motor to top speed, and a deceleration pulse returns it to rest. Motors don't use acceleration, though. They use voltage and current. Use too little, and the motion takes longer than it needs to. Try to use more than is available, and the motor can't follow the plan, resulting in large tracking error, overshoot, and a delay in finishing the move. Optimization finds the motion that is fastest and physically possible. It's not always easy. Velocity and jerk use voltage. Acceleration uses current. Friction and damping also use current, so that constant acceleration may use more current at high speed than at low speed. In this move, current goes right to the limit, and voltage is close, limiting the top speed. Teragamma's unique and patented technology automatically finds the combination of parameters that minimizes motion time for any motion, any motor and axis, and any operating condition. So let's get started. Today we're going to try to optimize motion for many small steps. We'll load a pre-made script and edit. This script moves 5 times in the positive direction and 5 times back again. We'll change the length of the step motion to 1 motor revolution, and we'll change the dwell time so that it pauses 50 milliseconds after each step. Give it a name and save. Okay, now we enable motion recording, enable a servo, and run the script 1 time. The recording window shows lots of things about the most recent motion. All items are available all the time. You don't have to select items to record. The entire script motion, not just each step, is automatically recorded up to 100,000 samples at full 10 kHz servo rate. You don't have to set any trigger conditions. That's the benefit of high-speed Ethernet communications. The entire move took 773 milliseconds. We'll look at a plot of the whole motion. Here are the 5 steps up and 5 steps down, and the velocity. And here's the position error shown during the settling phase. Teragamma software also divides the motion into steps and analyzes each one. Here we can see the maximum step time is 22.3 milliseconds. The maximum settling time is 1.2, and the maximum total 23.5. We can see a plot of all of the steps normalized and laid on top of each other, so you can see the variation in motion. Time 0 marks the end of planned motion and the beginning of the settling phase. Planned motion takes 22.3 milliseconds. Here's the motor is entering the in-position band, by default set at 5 encoder counts, at 1.2 milliseconds. For many applications, not only do you want the position error to be small, you want it to be stable. And here it is still moving. So we're going to set the in-position band to be 1 encoder count, where it looks like things are pretty stable. So we'll bring up the envelope dialog, set the settling distance to 1 encoder count. Immediately the recording dialog shows that the max settling time is now 6.8 milliseconds. And we can see that result right here. Now let's see how to make adjustments to the planned motion. Our goal is to reduce the maximum total step time. Right now it's 29 milliseconds. We'll display the limits window. And the first thing we can modify is the acceleration shape. There are trapezoidal shapes ranging from 0% acceleration to 100%, triangle to square. There's a smooth quadratic shape, as well as two proprietary shapes, plus and plus plus. So let's start with the triangle shape. Enable control and run the script. Here we see the plan motion has gone way up to 30.6 and the total step time has gone up to 33.6. We'll try more acceleration. And the plan motion is now 25. The maximum total step time is 31.8. We can try the quadratic. And here we see the results. We can also look at a script that runs a bunch of different shapes. This script goes plus and minus 1 motor revolution with shape plus, quadratic, and 3 different trapezoids, 95% acceleration, 60%, and 0%. We'll run it. Let's see what that looks like. Here we can see the 5 different motion times for 5 different shapes. The settling time doesn't seem to be affected very much by acceleration shape. You can also adjust the step type. By default, deceleration can be larger than acceleration. This allows friction to stop the axis for faster motion. If you like, you can insist that deceleration and acceleration are equal, that are balanced. Now we'll reload our 10 steps. Now the maximum step time is 28.4. If we go back to unbalanced, it's 26.7. You can also adjust individual motion limits. Normally that's just going to make the motion slower, but maybe that's what you want. We'll set square acceleration so that all the limits will take effect. The acceleration by default is 7.5 milliseconds to full speed. Let's change it to 20 or so. There. And the jerk, the time to maximum acceleration right now is half a millisecond. Let's change it to 2 milliseconds. Okay, now we enable control, run the script. And we can see that the plan motion time has gone up to 33, settling time is less, and the total step time is larger. The limits window only shows 4 trapezoid shapes, but the software supports any acceleration fraction between 0 and 100%. How do you find the fastest shape? Well, first we'll remove the manual limits, and we'll use this pop-up menu item to do the work for us. In this case, 91.6% is the fastest motion. Let's try that out. Now we see the maximum step time is almost as fast as Shape Plus. You can display the motion settings using that pop-up menu item. This is useful if you need to program an external motion controller with the optimal parameters determined by Teragamma software. Here it shows peak acceleration and jerk. This is for acceleration and deceleration. Step moves use high peak current. If the duty cycle is too high, the motor can overheat during continuous operation. Teragamma thermal modeling automatically finds the current limit for a motion script that ensures safe, continuous operation. We use this pop-up menu item to do just that. In this case, we find the current limit has gone up from 4.59 to 5.74 amps. So this motion is safe in continuous operation. Now let's change the dwell time from 50 to 10 milliseconds. Run the script. And now the current limit has gone down to 4.07 amps. We can find the acceleration and jerk settings that correspond to this limit. Okay, we've modified the planned motion Now let's work with closed-loop position control. Teragamma software supports up to 7 independent position controls. Each is active for a defined motion phase. By default, self-commissioning synthesizes 2 controls, a tracking controller, active by default, and a regulator, used to hold constant position. We're going to adjust the regulator to try to reduce settling time. You can adjust the bandwidth, damping, patience, which is a measure of integration strength, as well as various filters which we won't touch today. First, let's see the effect of reducing the bandwidth. We'll go all the way down to about 50 Hz. Notice that as soon as we change the controller, instability protection is automatically enabled. Now we'll run the script. We can see that the max settling time has gone way up. Let's look just at the settling phase to see why. And this is the reason. Some of the motions never settle at all to the in position band. Let's revert to the original position controller and adjust patience. You can adjust the position controller continuously while you're moving the slider, even during continuous motion. Watch the max settling time as I make adjustments in patience. Let's try one more thing. The tracking controller is still active for a defined settling time after planned motion completes. That settling time is set by default in the envelope configuration window to 5 milliseconds. Let's change the controller so that the regulator is active for this phase instead. We'll run the script. Now we see the max settling time is 12.8 milliseconds. And that's just what we see right here.
You've just seen a brief overview of Teragamma motion adjustment tools. They provide unprecedented power and usability to allow anyone to easily adjust servo motion. In the end, however, we weren't able to improve the motion for our application. Why? Because Teragamma self-commissioning has already done everything I've shown you today and much more, automatically and autonomously. That's real power, not having to optimize at all. I'm Chris Cullen for Teragamma Motor Control. Thanks for watching.